Hi. Howdy, folks. Welcome back from the break. We just finished up our sort of segment on all things ZK and privacy. And moving on, we're about to hear our next couple of sessions all about performance. We're going to start with some performance features that we've just implemented, talk about how those work. And then we're going to also end with Nico talking about some forward-facing, more research stuff we got in the pipeline. So without further ado, let's get started. So our first presentation in that sort of performance section is myself. So my name is Garand, and I'm a core engineer here at the Stellar Development Foundation. And today, I'll be talking to you about smart contracts through conflict-free parallelism and protocol-level caching. Let's get into it. So today, I'm going to first start by giving a high-level overview of some of the performance enhancements that just launched with Protocol 23, now known as WISC. So I'll give a high-level overview and talk about how those work. Next, I'll take a little excursion over to Shanghai and discuss an attack that happened on the Ethereum network, actually, and talk about what we learned from that attack and how that particular DOS shaped some of our design decisions in WISC. Finally, we'll conclude by actually talking about the results of those performance enhancements through some TPS numbers, some experimental results, and also show you all what you can expect to actually see and feel with these protocol upgrades on mainnet. So WISC is live. This was by far the biggest protocol upgrade we've had since we actually launched smart contracts earlier this year. It had a whole range of features. It had some scalability features, such as cap 70, that changed the way we do SCP timing. It had lots of usability features, like new host functions, as well as unified events, making the developer story for Stellar as easy and as it's ever been before. But what I'm going to be talking about today is all of the smart contract performance execution that happened. So let's talk about it. There are kind of three primary features that we shipped, but the overall category is this. Across the board, smart contracts just got faster and cheaper. We accomplished this first by introducing parallel transaction execution with cap 63. Essentially, prior to Protocol 23, we just executed one transaction at a time in a sequential manner. But with cap 63, many transactions can now be executed at the exact same time. This greatly increases the instructions that we're able to put through the network, as well as makes our transaction throughput faster and higher. Next, we have in-memory state via cap 62 and cap 66. These essentially remove disk reads from almost all smart contract invocation. What this does is not only eliminate disk reads or read limits and read fees, but again, greatly increases the transaction speed and throughput. And finally, we have the reusable module cache via cap 65. This essentially removes the expensive setup costs from contract invocation via keeping instantiated modules in memory. And again, as is the theme of the day, makes everything a whole lot cheaper and a whole lot faster. So let's get into it. First, parallel transaction execution. So to kind of set the stage for how this works, I want to give a very simplified example. In our example, we're going to have Sally. Sally is an art curator, a digital art curator, and she is tasked with buying the most exclusive NFT drop for her client. And so we're going to have these three characters. First, we have our NFT minting function. Then we have our middle person, Sally. And finally, our highly sophisticated NFT art collector. And so we're going to model this interaction with two transactions. First, we're going to have Sally minting the NFT in transaction 0. Sally is going to then receive that NFT. And then she is going to, in a separate transaction, send this to her client. Now, I know in practice, this isn't actually how this would happen. You wouldn't want to have a middle person here. You'd probably condense both the minting and the submitting into a single transaction. But just for the sake of argument, pretend that these actually do have to be two distinct transactions. So let's analyze how this is scheduled and executed on the network. So whenever the network finishes consensus, each validator receives a transaction set. This is the set of transactions that will then need to be ordered and executed by each validator on the network. And so in our example, our transaction set looks like this. We're going to have transaction 0, which is Sally minting our NFT. Then we're going to have Sally actually submitting that NFT to her curator. And because this is the actual entire network, we're going to have a lot of other transactions mixed in there too. Because it's Stellar smart contracts, all those other transactions are probably going to be farming Kale or something. And so this is our transaction set for the block. Now, in Protocol 22, we then need to schedule this on a single execution lane. And so here we only have a single thread and a single lane. And so it's pretty easy to schedule and execute this stuff. The validator is just going to pick transactions pretty much in order and then execute them one at a time. So first, we're going to mint our NFT. Then we might farm some Kale. And finally, we're going to send that NFT to our art collector. This is what it looked like in Protocol 22. Now let's talk about how we do this in Protocol 23. And so we're going to have our same transaction set that we had before, but instead of having one execution lane, you're going to have many parallel applying threads. In this case, I'm going to model this with 2. Now the question becomes, we have 2 threads that are doing things at the exact same time. How do we schedule our transactions? First, I'm going to demonstrate a naive solution. Just schedule a transaction in whatever lane has capacity. And so we're going to kind of just randomly pick transactions and throw them somewhere. And so we might, in the top lane, farm some kale, then mint our NFT, and then farm some more kale. And then at the exact same time, in our bottom lane of execution, we are then going to farm some kale, then we're going to transfer that NFT, and then farm some more kale. However, this creates a significant problem. Both execution lanes are happening concurrently with no synchronization in between, which means that each transaction is happening at the exact same time as the other one. And so we have a conflict. We have Sally trying to submit her or send her NFT to the art creator at the exact same time she's trying to create and receive that. Unfortunately, the Stellar network doesn't quite support quantum superposition yet. We don't have quantum validators. And so this is a serious problem on the network that we need to solve. And so in order to make sure that we don't have conflicting transactions and don't need any of these like semaphores or other concurrency constraints, we need to schedule our transactions a little bit smarter. So this is how we actually do it in Protocol 23. And so we're going to have our same transaction set as before, and we're going to have the same number of execution lanes. But instead of naively just scheduling a transaction in any lane that has space, we're going to make sure that we cluster our transactions such that all transactions that have a read-write conflict are in the same lane. What this looks like is in our bottom lane, we're first going to put all of our kale farming, because again, there's a read-write dependency on the kale being farmed or planted. And then in our top lane, our top execution lane will now have our NFT minting and sending transactions. The reason why these 2 transactions need to be in the same lane is because they have a read-write dependency on Sally. The first transaction, the mint transaction, modifies her balance by adding the NFT, and the second transaction modifies Sally's account by removing the NFT. They have a conflict, thus they are scheduled together. Now, because each execution lane is scheduled sequentially, we now no longer have quantum superposition, and all of our transactions can execute just fine. So now let's dive into the actual sort of underlying mechanics of how this works, a little bit beyond this simplified example. And so Whisk implements what we call conflict-free parallelism. This is what I just described, where we guarantee that each execution lane has no conflicts with the other ones, such that each execution lane can be done totally independently without any locking or contention. We achieve this by including a static footprint of all keys with each Sorbonne transaction. This includes a read-only section of keys that will be read, and then a read-write section. You all know about this. You've been doing this since Protocol 20. The conflicting transactions are all scheduled in the same cluster. Note that a conflict means that 2 transactions are trying to read and write the same entry. If 2 transactions are only attempting to read an entry, but neither of them write it, there is no conflict, so they can be scheduled in separate clusters. Then we guarantee that all clusters are independent and can be safely executed in parallel. While the transactions within a cluster might conflict, no 2 clusters themselves conflict, so they can both be scheduled on separate lanes without issue. Now, the number of threads that we actually have, the number of execution lanes, is controlled by a network config. When we just launched Protocol 23, currently this is configured to 1, just for a safe rollout, so we don't actually have parallel execution live on the network yet, but all the code is in place, and so a future SLP will increase this and actually add parallel execution threads to mainnet soon. Now, each cluster can have up to ledger max instructions. Now, what this means is that in practice, the effective limit of your ledger is actually not your ledger max instructions like it was in Protocol 22, but rather your max instructions times the number of clusters you have. The reason this is possible is that the instruction limit is designed to essentially cap the amount of time that you spend executing a Sorbonne phase of your block. But because each cluster is actually executed at the same time, they can both individually take the maximum amount of time that you have in the network. This means that we've effectively increased the actual capacity of the network significantly, even though we haven't changed the instruction limit, because we've added this multiplier to it. Now, I want to say I have a lot to cover today, so this was a highly simplified explanation of how parallel transaction execution actually works. If you want to know the details, I'd recommend reading CAP 63, or my coworker Siddharth did a presentation at last year's Meridian that goes into the actual details. The scheduling isn't just clusters. We have this other concept called stages as well, and so I'd recommend, if you're interested, to read these more. Now, before I move on, I do want to make one caveat that just because we have parallel execution does not necessarily mean that the performance of the network will actually increase. To kind of describe why that's the case, I'll give another example. And so this is the exact same picture that we had before, but instead of having our minting NFTs, just suppose that our transaction set is entirely made up of kale. Now, even though we have two execution threads here, because each transaction conflicts with each other, they will all be scheduled into the same cluster. And so we see here that even though we have two execution lanes available, only one will be used. So I want to make it very clear that the theoretical maximum number of instructions that we can process has increased, but that doesn't necessarily mean in practice we'll actually achieve that cap. It depends entirely on the actual transactions we have. And so Soroban is now capable of processing many more transactions if they are diverse. But if all the transactions are from one contract or of one type, then we may not actually yet have any benefits from parallelism. So something to keep in mind. OK, that's conflict-free parallelism. Now, let me move on to our second feature, in-memory state. Now, before I get into the details of how our in-memory caching works, I want to go back a little bit and give some background on state archival. And so state archival is our solution to the state bloat problem. State bloat is a problem that affects not only Stellar, but every public blockchain. So Ethereum, Solana, everyone you've heard about. Essentially, the issue is that all validators must store every single ledger entry indefinitely. It can never be deleted. What this means is that over time, meme coins and spam slow down your databases because someone will pay a one-time gas fee to mint them, but then the person who owns that meme will never actually take the effort to delete it. There's no reason for them to. So what this introduces a significant issue where you have your useful entries like your USDCs, your EuroCs and whatnot, who are competing for space and capacity with your memes and your spam. And so state archival solves this by charging rent. Essentially, instead of paying a one-time fee, every single entry must pay a reoccurring fee in the form of rent to stay live on the network. If an entry is not paying its rent, it becomes archived, and archived entries cannot be used by any transactions. But even if an entry is archived, nothing is actually gone. It can always be restored and used again. This is just background. Y'all know this. We've had rent since Protocol 20. But even though we've had rent in the state archival system, and y'all have been paying the fees, you haven't actually seen any benefits from it. That is, until now. So enter in-memory state. So state archival in and of itself doesn't actually really help us at all. It's just more fees and kind of a complicated restore and archival system for contract developers. However, it does enable tons of optimizations that have finally landed in WISC and Protocol 23. And so I want to make a couple observations about some properties that state archival gives our network. So first, we observe that only live state can be used by an invocation, with the exception of restore, which is an edge case we'll talk about in a bit. But for contract invocation, if they touch an archive piece of state, they immediately fail. Additionally, this allows the protocol to distinguish in a decentralized way between what is useful state and spam via this rent system. If something is archived, by definition, it is not useful because it can't be used in an invocation. It would just automatically fail, whereas live state is useful. This is much better than having us whitelist asset classes. We don't want the network to say USDC is useful, but some other asset is not. Rather, it's decentralized and organic. If there is an economic demand for an asset to have rent paid for it, it will be deemed useful by the network. There's an additional property where we are also able to cap the amount of live state to a fixed size. We do this via dynamic rent pricing, where we have a target live Soroban state size, and if that size is exceeded, the price of state exponentially increases, effectively giving us a cap on the live state. Now, if we combine these two observations, that we can distinguish between useful and useless state, and that the amount of useful state is capped, this allows us to safely mean that all useful state can be stored in memory. And this is what we do in Protocol 23. Now, all live state is in memory, which means that smart contract invocations no longer require disk reads in most cases. This allows us to completely remove read fees and read limits because in-memory access is just so much cheaper than disk access. So not only can you all do more, but you have to charge less for it as well. Now, there is an asterisk here, and so there are a couple of cases where we still need disk reads. So first off, restores require disk reads because those are actually still going to disk to get the archived information and bringing it in memory. However, these are relatively rare, and in Protocol 23, they're also automatic thanks to auto restore, so they're a whole lot easier to deal with. Additionally, because classic entries don't have a rent associated with them, we still have to charge disk fees for them. It wouldn't be safe to store classic entries in memory because they could grow unboundedly and cause us to have expensive validators, killing, and things like this. However, classic entries are relatively small, especially compared to Sorbonne state size, and so the fees and the disk hits that we have on these is still relatively low. So this is at memory state. And now moving on to our final optimization, which is the in-memory module cache. And so we can essentially extend the exact same concept to in-memory state and extend that to the actual contract modules themselves. For a little bit of background as to what a module is, before execution, your WASM code needs to be parsed and essentially translated into something that can be interpreted by our WASM interpreters, and it can actually be executed. Now, previously, parsing was required for every invocation. It was actually very expensive. About 80% of the total instructions used by all Sorbonne transactions were only for this sign of setup step. We actually didn't get to your code until very late into the process. However, we can observe that contract instances also have to pay rent, which means that they are also applied to the same theorems that we just had for the contract data. The result is we are able to parse all contract modules a single time on startup and then store those in memory permanently until they are, of course, evicted if the contract instance runs out of rent. The result is that we have greatly reduced the cost of smart contract invocations. Most of the time, invocations have been reduced by about 50 to 80% of instruction cost. Again, this requires absolutely no changes to your contract. It's the exact same code in Protocol 23, just got 80% cheaper in Protocol 23, or Protocol 23. And so this not only creates a smaller cost, but greatly increases the throughput and TPS that we are able to achieve on the network. And so that's essentially what we've done on Whisk. And now I want to take a step back and go on a small excursion to Shanghai and use this case study of the Ethereum attack to give a little bit more background as to why we have made some decisions that we did with respect to the Protocol 23 design. All right, let's go to Shanghai. So in the 2016 Ethereum DevCon conference, there was a massive attack that took out almost the entire Ethereum network. There were a few nodes that were still able to stay alive, but about 40 to 50% of stake actually went offline during this attack. Now the issue was an opcode, which is the EVM's equivalent of a host function, was mispriced. So essentially, there was this particular hashing function called xcode hash that actually had a computational cost of about 5 gas most of the time. The computational cost is the actual cost to the validator running the operation. Now, because in the average case it only costs 5 gas, the Ethereum protocol decided that it would charge 5 gas for this transaction. But the issue is, what about that 1%? 1% of the time, the cost of the computation significantly outpaced the actual cost that the protocol was charging. And so what happened in Shanghai is an attacker essentially noticed this. They uploaded a malicious smart contract that was just a for loop on this one opcode that had a that exploited the 1% case. What they were actually able to do is essentially DOS all the nodes. Because the protocol wasn't charging enough for this opcode, it was consuming too much memory, and it was killing or destroying the memory resources on a large portion of the Ethereum network. Now, why am I telling you this? This is a strong lesson that all blockchains are adversarial and Byzantine. And so when we're making protocol upgrades and setting limits and costs especially, we must always assume the worst case. We can't use the average case or the best case to set gas prices. Otherwise, we are going to be attacked like Ethereum was in 2016. So why am I telling you this now? How does this relate to Whisk and Protocol 23? Well, I think the key takeaway is that we did it the hard way, right? So we implemented 2 features, caching and parallel transaction execution. Neither of these are new. However, I would argue that the way we did it is novel and much safer and much more scalable than how other folks do it on the network or on other blockchain networks. And so I'd like to take this time to answer some common questions I get and some common friction points with the Sorbonne interface. So first, why do we have rent? I was the guy that kind of started the whole state archival conversation, and I get a lot of complaints about this rent charge because no EVM or Solana has this sort of thing. But there is a reason we do it. Now, if you were just to use a traditional DB cache, like a Postgres or a Levels DB with some memory attached to it to cache recently used state, you run into some significant issues. And so if you don't have a protocol definition of what is useful and just use an optimistic definition, these are the things you can run into. And so we could have the Solana case. So essentially, Solana implements a probabilistic or an optimistic database cache. However, because the protocol itself doesn't make a distinction between live state and archive state, they are forced to cache everything in memory. What this means is that to run a Solana validator on mainnet, you need about 512 gigs of RAM, and this has been increasing over the years as new state is added. The reason is Solana wants to increase their limits, assuming that state is cached. But because they don't have a distinction, everything has to be in memory. Otherwise, they could be attacked like Shanghai. And so they have very high cost of operation. The alternative is that you could use a partial cache, like a random eviction cache, and say, I'm only going to use 10 gigabytes of RAM or some reasonable amount of our cache. And then this will cover the USDC case and the case where most of the useful information will be in RAM. However, again, this isn't safe. An attacker could always observe what's in the cache and what's not in the cache and have malicious contracts that all require disk reads and all result in cache misses. This means that if you have a partial cache, you are actually not able to safely raise limits, and you must always assume that you are going to have a cache miss and require disk. And so with state archival and in-memory state, we're essentially able to have our cake and eat it too. We can keep our memory limits very low. We only require 16 gigabytes of RAM to be a validator today, but still maintain the high limits that you see on someone like Solana that has very high RAM requirements. And so this is why we've decided to do the rent system to maintain this protocol level cache, which is much more efficient and scalable than a non-protocol optimistic caching scheme. Next, let me talk about parallel execution. Why do we have footprints? They add overhead to the transactions. They make them larger and more expensive. There's also this annoying pre-flight or prefetching or simulation step where you have to pre-flight a transaction in order to determine what keys it will touch. This adds friction to the process. Why do we do this? We could just do something like optimistic concurrency instead, and it would be a whole lot easier. Let me describe what optimistic concurrency is and why it's also not very good for scale. So many other blockchains use something called optimistic concurrency, which essentially is where the validator assumes that none of the transactions will conflict. What it does is it takes a static snapshot of the ledger state at the beginning of the block, and it executes all transactions in parallel against that snapshot and pretends that there's no read-write conflicts. After it executes them all in parallel, it then retroactively checks if any of those two transactions in the set actually modify the same entry. And so if no transactions conflicted, then you're fine. You did all your parallel work, and you can just move on to the next block. However, what if two transactions did conflict? What if we had the Sally minting and sending an NFT example like we had before? What do we do in that case? Well, in an optimistic concurrency environment, you have two selections. Basically, you can either throw away all of your parallel work and re-execute the transaction sequentially in order to resolve the conflict, or you can pick one of the conflicting transactions and have it arbitrarily fail. Now, the issue is this provides a really poor user experience. If you pick the arbitrary failure case, what you're going to have is many users will see their transactions fail for no good reason. The transaction was valid, they paid the right fees, but they just happened to conflict with another transaction and lost a coin flip. And so you have lots of burned fees and unhappy users. Alternatively, if you do the optimistic approach where you throw away all your work and then re-implement or re-execute transactions that conflict in a sequential manner, then again, you can't safely raise limits. An attacker could always submit transactions that are all guaranteed to conflict, such that you have to be conservative and you can't raise limits assuming parallelism because you'd, again, be liable to a Shanghai-style attack. And so I think the takeaway from this is that I do understand that some of these features do add more, are a little bit more challenging to interact with in other blockchains. We have multi-dimensional gas fees, we have these footprints, we have these rents, and you're not going to see that in an EVM or a Solana chain. However, we're doing this stuff for a reason, and the reason is safety and scalability in the long term. All right, so finally, let's get into the good stuff, some results. So I want to first begin by observing a Kale transaction. This is a Kale transaction I took from Stellar Expert. It's got a bunch of text on the screen, ignore it. I want to compare the fees that happened for this transaction in Protocol 22 versus 23. And so on the top, you see the fees and the resources required for this transaction in Protocol 22. And at the bottom, you see the exact same transaction but executed on 23. These are both mainnet values, by the way. You'll see that across the board, everything got cheaper. the amount of disk reads went down, the amount of non-refundable fees went down, rent went down, instruction costs went down, memory went down. Every single thing you can measure got faster and cheaper. And so to be specific, Whisk is a massive improvement both in fees and limits. Instruction cost of every transaction reduced by up to 80% because we removed that expensive setup step via module caching. We have a 10x reduction in rent fees because of the in-memory state optimization. We have completely removed the read bytes limit for smart contract state, and for most invocations that don't require a store, because we store everything in memory. We've also been able to reduce write bytes fee significantly to a flat rate, further based on the in-memory optimizations. And while this also, in the short term, will make fees much cheaper, in the long term, we have much more capacity now to increase SLPs, or to increase network limits in future SLPs, and increase the amount of transactions and the complexity of transactions that Stellar can now handle. And finally, the moment y'all have been waiting for, TPS. Everyone loves to talk about TPS, and so I had to include a slide on it. That being said, I don't really like TPS. I think TPS is a pretty bad metric. Every network has a different definition of what a transaction is. Everyone measures it a little differently, and so I want to give something a little bit more concrete. So in this particular presentation, because we're talking about Soroban, I want to measure TPS via a Soroban sort of minimum amount of work, and I'm defining the minimum amount of useful Soroban work to be a SAC payment. And so for the purposes of these measurements, instead of describing transactions per second, I will be describing SAC payments per second, where all of these are in the native XLM asset. And so further caveats, all these measurements are applied time only measurements. They are not network-wide. They don't include overlay. They don't include consensus. These are only the time it takes to execute the transaction and write the results to disk, right? And so I don't want to look on Twitter tomorrow and see people posting about how Stellar is going to have 100,000 TPS tomorrow. That's not true. These just demonstrate the execution limits and the execution capacity of the Whisk protocol itself. So in Protocol 23, with a single thread, we're able to achieve about 4,200 SAC payments per second. And then with a multi-thread environment with 32 threads, we're able to achieve 12,000 payments per second. Now these numbers are significantly higher than what we saw before, but there still is a lot of room to grow. And there's lots of low-hanging fruit and bottlenecks that we're going to solve in future point releases. So a couple of reasons why these numbers are still, in my opinion, fairly small is that there's lots of work that's still sequential. So while the actual smart contract invocation itself, the smart contract code and the host functions are parallel, there's actually lots of work that happens before and after the transaction that are still in a single thread environment. This includes things like checking signatures, charging fees, emitting meta, and all these things that are still single threaded. Now again, these are implementation shortfalls. These are things that we can change and will change in upcoming releases. Some of this can be changed without a protocol upgrade even. And so there is always more work to be done. One final caveat on these numbers. This measurement was taken using batch contracts. What that means is that a single contract invocation sent many SAC payments. These numbers had one transaction sending 100 SAC payments each. Now again, they were sending them all from different addresses to different addresses, and so they are still realistic of like a STP, for instance, use case, or an institutional payment use case. But because of the bottlenecks that we see in the pre and post apply phase, we would not be able to handle 12,000 individual Soroban transactions for full transparency. So we've definitely seen an improvement. There's still a long way to go, but I'm very excited by what I've seen with Protocol 23 and Whisk so far. So I think I have 1 or 2 more minutes. If anyone has any questions about Protocol 23, anything I've talked about, or anything that's coming in the future, I think I have a couple of minutes. Yes, no? All right, I think we're good. Thank you very much.
Yeah, so if anyone has a question, one back there.
A great presentation. Just a quick validator thing on you're discussing, we haven't increased the throughput yet, but we plan to in the next 3-6 months. What would it look like for an average validator? How much more RAM or CPU do we need to add?
Yeah, so I think there's kind of like a short-term and medium-term answer to that. In the short term, like in this upcoming SLP, there will not be any changes to validator requirements. The reason being, we're currently using one thread, and our minimum requirements to a validator are already multi-threaded. I mean, any modern server has more than one thread on it. So in the short term, there won't be any enhancements. Now, longer term, if we see large volume increases, then there might be a conversation around raising validator limits. So for instance, in my numbers, I ran 32 threads. The reason I did that is that's the minimum core count required by Solana, and so I wanted a little bit more of an apples-to-apples comparison. But we're not going to require 32 threads in a month, and that will be a longer conversation that involves the validator community and the Stellar community as a whole.
Awesome. Well, thank you, Garand. Great work.
All right, thank you.
For Garand. Thank you.
Thank you very much.